Hi. So the majority of this lesson is going to be starting page 43 and page 44 and page 45, but you've got a blank page on page 42. It was going to be for something else, but I think it'll be a good place to stop and do some notes here and just follow me, get some notes down on where we are so far. So we've got two models, or other words I use to describe models are concepts, to describe different things that are moving in physics. We've got a constant speed model and a uniform acceleration model. The constant speed model has three different bits to it. The first is that we have a motion map. And so something moving at a constant speed has even gaps every second and the same size velocity arrow. Velocity, 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 velocity. That's one way to describe something with constant speed. A second way is graphs. And so we could have a displacement time graph. Something moving at a constant speed has the same gradient all the way up. And if I wanted to draw its velocity time graph, it is a horizontal line because its velocity doesn't change. The way we get from a displacement time graph to a velocity time graph is we find the gradient. The rise over run of this will tell us what the velocity is. We can go back the other way and we can, from the velocity time graph, if we work out the area underneath, we can work out the displacement area. So that's two pretty important ways of getting between these two graphs. That's a second way to describe constant velocity. Motion maps, graphs, and the third way is we've got an equation. And we come up with this equation ourselves when we did our experiment with the little buggies. And the equation we ended up coming up with was velocity is displacement over time, or displacement equals velocity times time. And it's really important that this is only used for constant speed or constant velocity. Then we looked at uniform acceleration. So these are the ways to describe it. We also, what experiment did we do? To start with here, we had the buggy. It was driving along the ground. Man. Here, our uniform acceleration, what we had was we had the ramp and we had the rolly boy. It was rolling down. That's my attempt at a rolly boy. And he's trying to spin around. I'm not very good at spinning him around. And he goes spinning, 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 and he goes faster and faster and faster and faster. That was our experiment. We have three ways of describing acceleration. We have a motion map. Something that, and let's draw our rolly boy rolling this way. So it lines up with the motion map. The rolly boy goes further and further each second. So velocity arrows get bigger and bigger. And in between them, we can draw our acceleration arrows. And they're the same size and the same direction. That's what uniform means. So that's one way we can use to describe acceleration. The second way is graphs. Same thing, displacement time, velocity time, and acceleration time. When things are accelerating, they don't have the same gradient in the displacement time. It gets steeper and steeper and steeper. The velocity increases. It looks like that, and the acceleration is uniform. Same here. We can take this gradient, if we wanted to work out the velocity. We can go a step further. If we want to know what the acceleration is from the velocity time graph, we can look at the gradient of the velocity time graph. And if we want to go back, same with this one here, we can work out the area under here if we wanted. It would give us the displacement. In this case, it's a triangle. We'd have to work that out. And the same going back here. You can see the pattern. if I wanted to, I could work out the area of the acceleration time graph, and that would tell me how the velocity's changed. Now, just as a heads up, this is calculus. Calculus is differentiating is working out the gradient, and integrating is working out the area. The third way you've got to describe uniform acceleration is equations. Now, this was up here as the equation for constant velocity. The equations for uniform acceleration are velocity final is equal to velocity initial plus acceleration times time. We have velocity final squared equals velocity initial squared plus 2AD. We have D equals velocity initial times time plus half AT squared. And we have another one which is distance equals velocity initial plus velocity final all over 2 times time. You can't go ahead and use this constant speed one as a when you've got something that's accelerating. You've got to use one of these 4 equations. The reason there are 4 is each equation has something missing. This equation doesn't have a D in it. This equation doesn't have a T in it. This equation doesn't have a final velocity in it. This equation doesn't have an acceleration in it. So you, depending on what you want, what you've been given, you can use any one of these 4 equations. Now, start off with people who are like, well, why don't I just use the equations? It's why would I care about all these graphs and everything? In the last lesson, well, in the last video, you saw that the graphs were awesome for understanding. They showed you that when I was throwing the ball up and it came down again, this point at the top, the acceleration was not equal to 0. The only way I could do that was with the graph, and that acceleration graph looked like this or something. So graphs are awesome for understanding. Motion maps, although they're really simple, are so great for figuring out what's positive and what's negative. Figuring out positive and negative. Now, is acceleration positive? Does it change? Is the velocity positive? Does it change? Does it become negative? So each of these is so important in their own right. And most people just, unfortunately, deal with the equations and they forget about the ones and the twos. Okay, so I'll let you copy that down. I might just finish this video here and make a new video for the next page. But copy that down onto page 42. It's going to be very useful for when we go on to page 43.